Hey, Algebra 1. Hope it's going well. I just wanted to preface this lesson by saying sorry that this isn't in color and that you have to put up with watching a video full of dull grays and blacks and uh, white and all that boring stuff. So sorry that the visuals are not going to be as thrilling and exciting um, as usual with all the vibrant colors we usually have. But I'll go ahead and draw in some exciting colors so that it's more flashy for you. So today is lesson 4.3, which is patterns and nonlinear functions. All right, our objective is to identify and represent patterns that describe nonlinear functions. All right, so we'll just go ahead and jump into it. The main thing for this is that a nonlinear function is a function whose graph is not a line or part of a line. Okay, if you look down underneath at this take note box with the concept summary linear and nonlinear functions, you'll see that the top three up here, these are all linear because they go in a straight line, whereas the bottom three down here are nonlinear because they do not go in a straight line, right? This one, even though there are a couple straight lines in it, it is not a linear function. All right, so we'll go ahead and look at problem 1 here. This is on page something 47. I think it's 247. Yep, 247. All right, so we'll look at problem 1. This is about pizza, which most of us like, so yeah, exciting. I can tell your mouths are probably watering just thinking about it. We have the area A in square inches of a pizza as a function of its radius r in inches. And then the cost C in dollars of the sauce for a pizza is a function of the weight W in ounces of sauce used. Graph these functions shown by the tables below. Is each function linear or nonlinear? All right, so we have this one right here is our area in square inches of a pizza. All right. And we know it's a circle pizza, because it says radius. All right, and a radius tells us half of the diameter of a circle. All right, so, or you could also say the length from the midpoint or the center of the circle to any edge on that circle. All right, that's what the radius will tell us. And then, so we've got that one, and then we've also got on the other side our table for the cost of the sauce. All right, so we'll go ahead and look at those. Down here, they went ahead and graphed them for us, and this is how you're going to look to see if one is linear or nonlinear. This is going to be one easy way to do that. All right, so like I said, I'd get us some nice vibrant colors since we don't have any. So here's our rainbow writing. So a linear function will be graphed in a straight line. All right, and then a nonlinear function is going to be not a straight line. Okay, we said that earlier. I'm just rewriting it just to really pound that information right into your heads. All right, this means because of this, a good way to tell is to just graph your functions. Okay, so if you're just given a table, if you want to know if it's linear or nonlinear, you can just graph it. That's going to be a great way to be able to tell. So they went ahead and graphed these ones for us. All right, so you can see here the pizza area is not a straight line, right? It curves upward here. All right, so that one is going to be a nonlinear function. All right, and then the sauce, the cost of it is a straight line right here, as you can see. So the function is linear. All right. Okay, so another way that we can tell if one is linear or nonlinear and I think we may have seen this in the last lesson, but I don't remember for sure. You can look at the difference between each value. All right. So if I look at the sauce cost here, the difference between the values of 2 and 4 is 0.8 or 80 cents on this occasion. And then 4 and 6, that's 0.8. 2.4 and 3.2 right there, that's 0.8. And 3.2 and 4.0, that one's 0.8 as well. All right. All of these, the difference for all of these is also going to be 2 every time. All right. So since these numbers and these numbers are all the same, that means it's linear. Okay. That is another way that you can tell without having to graph it. All right. So if they're the same difference between the numbers on each of them, it's going to be a linear function. And then on the flip side of that, over here, we're again going by 2 each time. So we've got 2 there, 2 there. This one, I don't know what that is. That's what, 4780 or something? So 47.8 maybe. Nope, 47.7. And again, I'm doing that mental math, so if I'm off, sorry about it. And then we go from 2 there. And then this one, I don't know what that is. It's something like 63. All right. So since these two are different, while these two are the same, this one would have to be nonlinear. Okay. All right. So that was a lot of information. You can kind of pick and choose which stuff you really want to use, right? So if you prefer to do the graphs and only do the graphs, at this point, I'm kind of okay with you just checking from the graphs. If you prefer to do it in the tables and actually look at the numbers of it, that's also fine with me. You just choose whichever way you want to do it is fine with me. And then I'm going to have you guys go ahead and do problem 1A in the Got It. All right, so that 1A problem, it says that you need to graph it. I'm going to go ahead and give you guys the option of graphing it or checking it the way I did with this. All right, so the checking the number or the differences in the numbers. So whichever way you want to do it is fine with me. Just make sure that you know how to do it and you do it one way or the other. Once you do that, resume the video. We'll get going again. All right, so here on problem 2, on the very next page, we have representing patterns and nonlinear functions. It says the table shows the total number of blocks in each figure below as a function of the number of blocks on one edge. Okay, so it asks you to find a pattern that you can use to complete the table and then represent the relationship using words, an equation, and a graph. Okay, so one thing that I'm going to just recall for us here is that whenever we have a 3D figure, all right, if you're going to represent like the size of a 3D figure, whether it be the surface area, really the surface area is the best example, but if we have a 3D figure and we're going to represent surface area, let's say if we look at this one, you're going to look at that as, it tells us the total number of blocks is 27. All right, so that would be like having, if 27 was a surface area amount, that would be like 27, we'll pretend it's centimeters, and then it'd be cubic centimeters. All right, sorry, I lost my train of thought. I was talking to somebody. But anyway, so if we have a 3D figure, we're going to represent it as cubed, not the surface area. I don't think that was what I think I said that. That's not what I meant to say, but the area would be cubed. And so that's kind of what you're looking at when you look at the total number of blocks. Since we know it's cubed or to the third power, that's kind of what I'm going to look at here as well. All right, so if I do 1 to the third power, I'm going to get 1. 2 to the third power is 8. 3 to the third power is 27. Okay, so that's going to be my pattern. All right, so I'm going to take everything to the power of 3. So whatever 16 times 4 is going to be right here, looks like it's 64. All right, and then for 5, 5 to the third power, or 5 times 25 would be 125. All right, and then they also wrote it down here as well, if that rainbow is kind of hard to read on that background there. So yeah, that's going to be the pattern that we're going to use for this one. All right, and then in words, so they have it here. They say the total number of blocks y is the cube of the number of blocks on one edge x. All right, and then they've got it in equation form right here. So y equals x to the third, or x cubed. Okay, and then you can use the table to make a graph. All right, so it says you can use the table to make a graph. The points do not lie on a line, so the relationship between the number of blocks on one edge and the total number of blocks is a nonlinear function. All right, again, it's nonlinear because the points do not lie on a line. All right, so if we were to start here at 0, 0, it goes there, 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 and you can see it curves upward. It's not a straight line. All right, so that tells us it's not linear. All right, moving forward, I would have you do, let's go ahead and do number 2. For a second, I thought it was the exact same example, just with something different. But no, yeah, it's the same example, or a different example. So go ahead and try number 2 out on your own, and then we will move on after that. All right, so the last part of this lesson is writing a rule to describe a nonlinear function. We kind of touched on it on problem 2. But we'll go ahead and look at this one as well. So the ordered pairs 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32 represent a function. What is a rule that represents this function? Okay, so the first thing you're going to want to do, just for organizational purposes, just go ahead and make it into a table, which they do for you right here. All right. And then you want to figure out what you can do to get x to y each time. All right. This one that they have for you, I think, can be a little bit difficult. But luckily they've done it for us. Okay. It's just a harder one to see if you're not being presented with it to begin with. Okay. So you want to check and see what those rules are. So the way that they go through it is that they say, what rule produces 2 given an x value of 1? The rules of y equals 2x, y equals x plus 1, and y equals 2 to the x power work for 1, 2. Okay, so that's one good thing to do, is just look at the first one and think about what rules could work for that one off the bat. All right, then they go into the second one, which is 2, 4. Y equals x plus 1. It says it doesn't work for 2, 4, which is true, as you know. So we'll go ahead and cross that one off. And then we've got y equals 2x left. That one still works. And we also have y equals 2 to the x power, and that one still works. So then we can look at 3 and 8. Y equals 2x, that one doesn't work for this one. And then y equals 2 to the x, that would be 2 to the third, which does equal 8. So that's going to be the rule that we're going to want here. All right. So the function can be represented by the rule y equals 2 to the x power. All right. So I want you to go ahead on your own and try out problem 3. And then once you've done that, we will be done with this video lesson, and I will see you guys in class.